Hello everyone, this is lecture 10 and today we're going to talk about specific storage and gravity drainage. The learning objectives of this class is to understand the specific storage of an aquifer and the storage coefficient of an aquifer. And the second is to understand the gravity drainage process and the specific yield in relation to capillarity. And third is to derive a continuity equation for gravity drainage. So let's start. So first up is the specific storage, and in the aquifer, when the water is injected, the pore pressure will increase. So, but the total stress will remain constant. So from the relation between the total stress and effective stress and the pore pressure, as the total stress stays constant, so that as the pore pressure increases, the effective stress will decrease. So, and also as the water gets injected, the pressure will build up so that the water will compress, so that depending on the water compressibility, the water density will be changed. So this is related to the water compressibility. So as the pressure goes up, so in the confined space, you have more water is stored. And what about the effective stress? As the effective stress decreases, the soil matrix can expand. So this is related to the soil stiffness, or in other words, the compressibility of a soil matrix and the porosity. So as the effective stress decreases by the water injection, the soil matrix will expand, which means that the porosity will increase. So specific storage is the volume of water removed or added to storage per unit volume per unit change in head. So the definition of a specific storage S sub S is 1 over Vt times dVW over dH. So as you can see that the Vt over this is the water volume change, right? Water volume change over the total volume is the storage, the water volume removed or the stored per unit volume of the aquifer, right? And this is divided by the head change, which is dH. So the unit, so this is the total volume of the aquifer. So the unit will be, here the volume is divided by the volume, so it will cancel out. And so you have the head, which is in the length dimension. So the unit will be 1 over length. And this specific storage is also can be expressed in terms of the soil matrix compressibility alpha and the water compressibility beta and the porosity times the water density and the gravitation. So derivation from this equation to here is also described in detail in the handout. We're gonna go over the handout in the class later. And the second parameters that we're going to talk about is the storativity or coefficient of the storage. So storage over the entire thickness of an aquifer is defined or characterized with this coefficient, and this is the aquifer's property. So let's say that we have a thickness, the aquifer having the thickness of B, then the coefficient of storage S is SS times B. So in other words, that 1 over A times dVW over dH. So now it's 1 over A instead of the 1 over V total volume. So this storage coefficient of storage is a dimensionless quantity which gives the volume of water added to or removed from the storage per unit surface area per unit change in head. So as you can see, the difference is that because you multiplied the specific storage with the thickness of the aquifer. So it's we're talking about the unit surface area. So how to calculate the specific storage and the storage coefficient will be dealt, we're gonna compute together in the class example. And so let's talk about the gravity drainage process. So let's say that you have some original water table here in the aquifer, and the bedrock has some geometry like this, so which is the impermeable layer. So then if there's a rain or the water infiltration, then the W is the parameter expressing the water infiltration, so inflow rate from the infiltration. So then original water table will be changed by the gravitational drainage. Because of the drainage, if you have a slope, this water will just flow by the gravitation. So then this delta H is to be characterized. So we have to calculate this delta H, the change in the water table height. So here the H is the elevation of the water table above the datum, and this eta, the location of the impervious layer. So the H is a function of x and t, so with the distance and with the time it varies. But the eta is the location of the impervious layer, which is constant over time. So it just varies as a function of the distance x. So if a saturated soil is left to drain under the force of gravity, not all of the water is removed. Capillary force may result in the retention of water. The fraction of water volume which drains is called the specific yield. So, which means that as the water table gets lowered, not all of this water in the pore is get removed. Because the capillarity by the pore will hold some of the water, so you have some residual water saturation in the pore spaces. So then the water volume which is drained only is called the specific yield or drainage porosity. So that specific yield is defined as the gravity drainage volume over the bulk volume. And as you can see, the volume divided by, so the dimension of the specific yield is dimensionless. So if the water table is lowered by an amount of delta H over an area of A, then the volume of water drained from the soil is V drained, can be computed from by using this SY and delta H and A. So the fraction which is held by the capillarity force is called the specific retention, so that this SR is equal to N minus SY. So here the N is the porosity. So the last topic that we're going to talk about in this class is one-dimensional continuity equation for gravity flow. So we're going to derive the continuity equation for the gravity flow. So let's look at this figure, and let's say that we have an original water table here, and the impervious layer is here, it's flat, and for the delta x, this delta x, and we have a height of the water table, delta H, and in this element, or to this element, we have an inflow Qx and the outflow Qx plus delta x. Then consider the unit thickness of this aquifer. So to the direction of direction normal to this page, we have a 1 meter maybe thickness of the aquifer. So then continuity equation can be derived using this kind of a definition, so that rate of change of volume storage increase plus the net volume out is the same with the volume of source. So here the volume of source is like the infiltration rate maybe. So the somehow the water is coming and then injected to this volume by itself. And so from here, the rate of change of the volume storage increase is Sy, the yield, specific yield, times delta H over delta T times delta X. So this is from here. So the volume of water drained is the specific yield times delta H times A, right? So here the delta X times 1 will be the area, the unit area for the delta X length. And the delta H is the height change of the piezometric surface. And the delta T is for the within the time frame. And plus the net volume out is for the flow rate. So Q x plus delta X minus QX. So here Qx plus delta X minus Qx is W times delta X. So the infiltration rate is has the dimension of L over T. The reason is that I didn't say it here before. It's a flow rate, but the volume of water coming in divided by the area and divided by the time. So L to the 3 divided by L to the 2, so it becomes L1, and then divided by time. So L over T is the dimension for the inflow rate, W. So here inflow rate has the dimension of L over T, and also you can multiply the delta X and the unit area at 1. So then this is the volume of water coming in. And here the Qx plus delta X is defined as the Qx plus round Qx over round X, which is the gradient, the Q gradient, and the delta, and multiplied by the delta X. Then here by you can simplify this equation to this final continuity equation, right? Sy times round H over round T plus round Qx over round X is W. Then let's use the Darcy's law to manipulate the equation. And then the Q is KIA. Here the Qx, we're considering the flow rate in the x direction, and K times H minus eta is the length from here to here, right? So that it gives you the area where the water is coming in. And the I is the hydraulic gradient, so the round H over round X gives you the Q. So then this Sy round H round T is round X, K times H minus eta times round H round X plus W. And this is a nonlinear second order PDE, it's a partial differential equation. So to solve, and we have to apply the boundary condition. So then we can get the H in terms of the X and T. Okay? So the objective to solve this equation is to get the piezometric surface, right? So H, the piezometric water surface with time T and distance X. So then let's assume the steady state or steady flow. So the round H over round T is 0, it's because the H is constant over time. So then the equation becomes the ordinary differential equation, ODE. And let's assume that the aquifer boundary is flat, and also put the datum at the base, then this eta becomes 0 because the datum is now at the base of the aquifer, right, here, and K is constant, so that's which is the hydraulic conductivity of the aquifer. So then here that equation becomes more simple, so this becomes 0, and eta becomes 0, so that equation becomes K times, and the K you can take out the K out of the parentheses, right? So K times d dx h times dh over dx plus w equals 0. Still it's a nonlinear equation, right? So we have to do something more, and h times dh over dx is actually 1 over 2 times dh squared over dx, because that using this chain law, right? So we know that the dy to the n dx is n times y n minus 1 dy dx. So using this relation, here the n is 2 in this equation, then you can manipulate and you can get this equation. So then this h times dh dx can be replaced with this. So then the equation becomes plus 2wk equals 0. So now it's we can solve this equation, right? So by integration, and here w is constant. So by integrating this equation, we're gonna get this final equation: h squared plus wx squared over k is a times x plus b, which is called the dp equation or the dp formula. Then to solve the a and to get the a and b, you can use the boundary conditions. So in the class, we're gonna talk about how to use these equations in some examples, like the flow through an embankment, and also when there's a original surface, the water table, and when we apply the drainage pipe with the distance L, then how this water table will change, right, will be discussed. And we're gonna solve these examples together using these dp equations. So in this class, we have talked about the aquifer properties, the specific storage and the storage coefficient, and the gravity drainage and the specific yield in relation to capillarity. And we said that there will be not all of the water will be removed because of the capillarity holds some water. And the continuity equation, and also we derived the dp equation, dp formula for gravity drainage.